In Module 6A and 6B, we will demonstrate how to perform a dynamic analysis using the modal superposition method. Modal superposition is one of two methods in Autodesk simulation multiphysics for performing transient response analyses of linear systems. This type of analysis is used when the loads are time-dependent and the system will respond to these loads in a dynamic manner. The modal superposition method uses natural frequencies and mode shapes to reduce the size of the problem. In this example, we will use the natural frequencies and mode shapes computed in Module 5. Module 6A, this module, will show how to apply loads and set the analysis parameters. Module 6B will demonstrate the tools available for analyzing the results. The model that will be used is the same cantilever beam used in previous modules. How the beam is meshed was demonstrated in Module 4A. The first step in setting up the modal superposition analysis is to copy the natural frequency design scenario. Next, we will change the analysis type to transient stress modal superposition. This is done by selecting analysis type, then set current analysis type, and modal superposition is an option within the linear area. A 5-pound load having the form of a step function will be applied to the free end of the beam. The manner in which loads are applied to node points in this analysis type is a little different than in other types. We have to set up a table in the analysis parameters section based on node numbers. At this point, we need to determine the node numbers along the top edge of the beam where the load will be applied. We will use the inquire option to do this. We will also only apply the load to the corner nodes of each element. It is not good practice to apply loads at mid-side nodes when the load is to be equally divided. We will zoom in to the end of the beam to better see the nodes as they are highlighted. The first node at the near corner has a node number of 2. The node at the opposite corner has a node number of 5. The nodes in between range from node number 393 to node number 407. With this information, we are now ready to edit the analysis parameters. The analysis parameters contain several different areas of information that must be applied. There is an area to define the event, damping information, load curves, and dynamic load data. First, we will create the dynamic load data contained in the table. Since there are 17 nodes that will have loads applied, we must first add 16 rows to the table. Notice that the index is incremented automatically as each row is applied. For each row, we must define the node number, load curve, the type of load, X, Y, and Z scale factors, and an activation time. We will demonstrate this for the first node number of 2. It will have a load curve of 1 that will be defined later in the module. The type of load to be applied is a 0 for a force and a 1 for a moment. We will be applying a force, so we will leave the type to 0. The X scale, Y scale, and Z scale factors are where we apply vector components of the load to be applied. We will be applying a force in the Y direction only, and it will be a 5-pound force distributed equally among the 17 nodes. This works out to be a force magnitude of 0.294. Since it will act in the negative Y direction, we will enter a value of minus 0.294. The activation time is used to activate the value and time at which the force will be applied. As a demonstration of this feature, we will set the activation time as 0.05 seconds. This information must be applied in each row of the table. We have just completed filling out the dynamic load data information and are now ready to define the event information. We will first define the time step size. The applied load will excite the first three modes associated with bending about the weak axis. The third weak axis bending mode has the highest natural frequency that will be excited. It was determined in Module 5 that this mode has a natural frequency of 492 Hz, which equates to a period of 0.002 seconds. We will use a time step of 1/10 of this period. This works out to be a value of 0.0002 seconds. We can also use natural frequency information to determine the number of time steps. The lowest weak axis bending mode has a natural frequency of 28 Hz, which equates to a period of 0.036 seconds. We would like to have at least 3 cycles of this mode included in the results. 3 times 0.036 gives a time of 0.108 seconds. The transient response won't start until we exceed the 0.05 second activation time. Therefore, our analysis must have a duration of at least 0.158 seconds. With a time step of 0.0002 seconds, this means we must have at least 790 time steps. We will perform the analysis for 1,000 time steps, which will give us a little more than 3 cycles of the first weak axis bending mode. We will also set the output interval to 2. This means that only the results for every other solution will be saved during the analysis. Next, we will define the load curve. The load curve defines a load multiplier that varies with time. Since we use the activation time to create the step function, we need a constant load curve. We have to add another row to the table. The first time will be associated with the beginning of the event, which will be time 0. We will set the factor to 1. This next time will be associated with the end of the event. Since we will be using 1,000 time steps and a time step of 0.0002 seconds, this gives a duration of 0.2 seconds. The factor associated with this time will also be 1. Notice that a plot is automatically created that shows the factor on the Y scale versus time on the X scale. Damping of 0.5% of critical will be applied to each mode. This is a representative value for a lightly damped system. The actual damping in the beam would have to be determined experimentally. Next, we must define where the modal results, natural frequencies and mode shapes, will be found. In this case, they are included in design scenario 1. At this point, we are ready to submit the analysis. In Module 6B, we will demonstrate tools for analyzing results. This concludes this video.